Okay, now let's quickly grim through certain types of vectors. The first kind of vector would be equal vectors. Now this should be very easy for you because we already had the discussion. The vector would be equal when the magnitude, the unit and direction, they all three are same. Like these two vectors, if they are representing force, then if I have drawn them of exact the same length, then the length is same, meaning magnitude is same, the direction is same, and if they are representing same physical quantity, then the unit would be also the same. Then these two vectors are equal vectors. Okay, now we can talk about parallel vectors. Parallel vectors, as you can understand from the name, parallel vectors will be the one which will be pointing in the same direction. These two vectors of course are parallel vectors because they are pointing in the same direction. But if I draw the third vector which is not of the same length, then still the third vector is parallel to both. The third vector is parallel to this vector, is parallel to this vector. All these three vectors are parallel to each other. They are parallel vectors because the direction is same, that's it. Anti-parallel vectors, as evident from the name, the vectors which are pointing in opposite direction. If this is pointing towards east, this is pointing towards west, then they are anti-parallel vectors. These are anti-parallel vectors. They all are, no, this vector is anti-parallel to this vector is anti-parallel to this vector. But these two vectors are parallel because they are pointing in the same direction. Similarly, collinear vectors. Again, it's evident from the name, collinear vectors would be vectors which would be lying on the same line. They would be linear. For example, this vector and this vector. They are collinear vectors because they're lying in the same line. Now, one thing you should understand straight away, and we should be able to figure out, and it should have occurred to your mind. What we studied a moment back was we can shift the vectors parallel to each other. Now, if these two vectors are parallel vectors, fine. What I can do is I can shift this vector parallel to it, like this. That is allowed because I have changed nothing. Neither did I change the length, nor did I change the direction. It is allowed. So, and again I can shift parallel to it itself, and again I changed neither the length nor the direction. So it's still pointing eastward and it still have the same length. So it's the same vector actually. So if the parallel vector that we just studied, they are actually, you can arrange them and bring them in the same line. So they will also be collinear vectors. But the point is, you cannot always do this. It is not always allowed that you can change the direction, you can shift the vector parallel to each other. It is not always allowed. Let me cite you an instance when it will not be allowed. Suppose you have a rod like this of length L, and it is hinged at this point. Hinged meaning it is like pinned at this point, and it can rotate along this axis. Now I have applied a force F. If I talk about torque, then we have done it before, that the torque represented by tau is force into perpendicular distance from the axis. Now this is the axis along which it will be rotating, and the perpendicular distance is this. Let me call this as R. Now the torque is F into R. Now if you go on shifting this vector parallel to itself and bring it somewhere here, then the distance from the axis will obviously reduce. In the torque calculation, the value would change because force remaining the same, but the distance from the axis would be reduced, so torque will be decreasing. Now that is not true. For the calculation, you cannot do that. Vector is here, it will have particular distance from the axis, there will be particular value of torque. Okay? If there's a particular value of torque, and if you shift the force parallel to itself, then the value will change. Then you don't have a unique value of torque, which obviously is absurd. So when we do the calculation, when we are interested in torque calculation, then shifting of force vector parallel to itself is not allowed. So in certain circumstances, like the one we have seen here, the shifting of force is not allowed. So in those cases, the parallel vector, these two are parallel vectors, but these two are not collinear vectors, because you cannot shift it like this and again shift it like this and bring them in the same line. This is simply not allowed. So all parallel vectors may not be collinear vectors. So, okay, so that's the difference there. Okay, and similarly, you'll have collinear vectors and we'll see coplanar vectors, let's say. Now again, evident from the name, suppose I have three vectors like this. They are planar, they're lying on the same plane. But if the third vector is like this, then they are not lying on the same plane. Two vectors will always be in one plane. These two vectors is in this plane, these two vectors are in this plane, these two vectors are in this plane, but all three are not in the same plane. So when the three vectors lie in the same plane, they are coplanar vectors. When they don't lie in the same plane, they are non-coplanar vectors. Okay, so if they lie in the same plane, they are coplanar vectors. Zero vector. When we go deep into the mathematics of this vector, as we'll do in a while, we'll see certain calculations. For example, you have a block, you have a smooth surface, and somebody is pulling this block with 5 Newton of force, and somebody is pulling this block in the opposite direction with the 5 Newton of force. Now in this case, the block is not going to go anywhere because the net force on the block is 0. 5 Newton this side, 5 Newton that side. What actually is happening, the net force, if we calculate, is 5 Newton minus 5 Newton, because the other 5 Newton is in just the opposite direction. So if we consider this as positive direction, then this will be the negative direction. So this comes as minus 5 Newton. So if we are calculating the net force, we have to add all of the forces. One of the force is 5 Newton and the other force is minus 5 Newton. And the net force comes out to be 0. Now see, to make it consistent, the sum of vectors should always be a vector. The sum of scalars are scalars. Sum of scalars cannot be a vector. Similarly, the sum of vector should come out as a vector quantity. Now the sum of vector here is coming out as 0. So in this case, the 0 should be a vector quantity to make the theory consistent always. Sum of the vector, even it is coming out as 0, it should be a vector. So we define it as a vector quantity. It doesn't make any sense because the magnitude is 0, so it's not going to affect anywhere, it's not going to come into the picture anywhere. But even though, since it is the sum of vector quantity, it should be a vector quantity. So we say this as a 0 vector. We define it as a vector, we do write it as vector, but it doesn't have any magnitude. So we call it as 0 vector or null vector.